Hello everyone, welcome to a joint CIGRE web-tute jointly hosted by the Australian and New Zealand mirror panels for Study Committee A2. My name is Ross. I am the outgoing convener of the Australian panel, and I am pleased to welcome Matt Gibson to you all to take over the helm as the new convener of the Australian panel. So with that, please, Matt, you can now run with the show. Thank you. Everyone enjoy.
Thanks very much for that, Ross. Yes, thanks very much everyone for attending today. Welcome to the next in our series of A2 web-tutes that are being jointly hosted by the New Zealand and Australian A2 panels. We've got a great lineup of international experts speaking for you today on the topic of measuring moisture in transformers and how to keep them dry. So the three experts we have. First up will be Dr. Ivanka Herlein. She's the current laboratory manager at Siemens and led the CIGRE D152 group on moisture measurement using capacitive probes, which was finalized in 2018. So Dr. Herlein will talk about the key points of moisture measurement using these probes. Then next up, we'll have Dr. Dan Martin, who was an Australian corresponding member on this D152 group, and since 2007 has led projects to improve the determination of water in transformers using capacitive probes with Victorian, New South Wales and Queensland utilities. So Dr. Martin will give an overview of his case studies for that work. And then to round it off, we've got Dr. Baba Das, and he's the lead digital business developer for transformer business units at Asia Pacific, Middle East and Africa at Hitachi Energy. He'll explain new digital techniques to keep transformers dry using state-of-the-art self-dehydrating breathers. And we'll also discuss the return on investment benefits upon adoption of this technology. So just a little bit of housekeeping before we start. If you could all please keep your microphones on mute throughout the presentation to avoid distraction for the speakers, if that be possible. And if you have any questions, please enter them into the chat window in the GoToMeeting box there. And also introducing Judith Marks, who's our NGN representative, and she'll collate these questions as we go, and after the three speakers are finished, we'll then get back to answering some of those questions. Yeah, so with that, I'll hand over to Dr. Ivanka Herlein to start the presentation. Thank you.
So hello, everybody.
Hi.
I'm hoping you are seeing my screen. Is it the case?
Not yet.
Not yet, no.
Not yet, okay.
Ah, yes.
And now?
Yes.
Yep.
Okay.
Yes. Yeah.
Very good. Just a moment to make it somehow bigger. It is a little bit strange too.
If you press the key F5 on your keyboard along the top, it should start playing it. Yes, that's good.
Yep, perfect.
And also of capacitive sensors for moisture evaluation in transformers, in transformer insulation. This is me. Everybody calls me Ivanka because I have a very long name. So I would like to talk today on several points, not on everything. We have we have written the brochure 741, and you can read a lot of things there. I'll concentrate only on certain points. First of all, I'll shortly talk about moisture in transformers. We must talk about that a little bit, where it comes from. Then on different measurement methods, Carl Fischer, the classical method versus capacitive sensors, and then how to evaluate moisture in transformers using capacitive sensors. Possible criteria for evaluating transformer moisture level. This is very important because up to our work, these criteria did not exist. Then, of course, if we have moisture in transformer, how can we mitigate it? And of course, at the end, several conclusions. So where the moisture is coming in a transformer insulation, there are several ways for that. First of all, of course, it can be residual moisture in the wooden cold thick structural components if the transformer has not been dried properly. It can come through poorly maintained or missing dehumidifiers. From ambient, it can be a rupture in a rubber bag or contamination from ambient air during open service, for example, or leakages. When something is coming out of the transformer, of course, air is coming inside and moisture together with it. And of course, aging of solid insulation can also cause moisture increase in a transformer insulation. And a transformer has a lot of solid insulation, and the solid insulation can be very thick, like clamping parts and laminated pressboard or laminated wood, pressboard cylinders, insulation paper, and all these materials have different thickness. And therefore, it is very important to know how moisture can move from one part to another. And moisture is like a phantom. That's why it's very, very difficult to determine it really definitively, because it moves from one place, from solid insulation into the oil and vice versa, depending on different factors, depending on temperature, depending on the thickness of this insulation which we're seeing here, depending, of course, on the amount of moisture. So that's why the question of moisture is very often very controversially discussed. But one thing is definitive and clear: if we have moisture, we have a problem. Where is the problem actually? Why are we so much afraid of moisture and try to avoid it in any way? There are two major threats. The first major threat is the immediate risk of breakdown in the insulating liquid itself. You can see here one graph which shows the dependence of breakdown voltage to the relative saturation. Why do we talk here on the relative saturation and we don't talk on absolute content of water? First of all, what is the relative saturation? This is actually the ratio between the dissolved amount of humidity at a certain temperature to the maximum amount of moisture at the same temperature. And this graph here is very good because it shows us different liquids with relative saturation. And we can see here that the graph is very, very similar. It will not be the case if we would have taken the absolute water content for these liquids, because they can solve different amount of water, absolute amount of water. But talking on relative saturation, we are on the same, actually, on the same plan. We can see here, even here already, that about up to 20% of relative saturation we have breakdown voltage, which is nearly the same at the very beginning. And this is an essential message, which we will see later on when we talk on criteria for capacitive sensors. The second big threat of moisture is not only the immediate breakdown in insulating liquid, but also the accelerated aging of solid insulation. We know that insulation paper consists of cellulose and hemicelluloses, and the hemicelluloses is something like glue which stick all the things together. And when we have oxygen, that means air, which we have on the earth, where we have temperature, what we have in a transformer, we have acids which develop out of the solid and liquid insulation, and we have humidity. We'll have accelerated aging of the solid insulation.
Yeah, I'm right.
How can we determine moisture? Actually, there are methods which are used for, I would say, maybe 100 years nearly. This is the Carl Fischer volumetric titration, which is a chemical method which is widely used by laboratories and by users. And it determines the absolute water content in a liquid. On the other hand, we have new technologies which have developed somewhere in the 70s for determining of moisture in air first. And in the 90s, this technology has been forwarded for determination of moisture in insulating liquids. This is the thin film capacitive sensors. In our working group, we dealt a lot with both methods because we tried to compare them. Actually, we had a round-robin test on Carl Fischer determination and thin film capacitive sensors determination for moisture. The time today is not long enough that I talk on that because it's I would say it's a webinar for itself. We dealt also in this group with a possible transfer of the values of relative saturation to absolute humidity. This is regretfully today also the time too short to talk on that. But what I want to show to you, please don't learn it by heart. You find it that in any IC standard, especially in the standard IC 6422. Of course, Carl Fischer measurement is still very important and very widespread. That's why you have the key values for water in mineral oil in such a standard. But at the same time, you see a lot of recommended elections, a lot of messages which tell you, please regard the moisture in the liquid always together with the breakdown voltage, because they are very interdependent. And the moisture in a liquid is very much dependent on the temperature, which is very, very difficult to be exactly determined in a transformer. But of course, this is historical, and this must be there still in order to give a guidance to the users. But what I'm happy to tell you today is that in the new edition of 6422, which is now at voting and at the national committees, we have now one of the major achievements of the working group, and that we have the percent saturation also as a kind of guidance for users. This is the first time where online monitoring is really directly included in a standard. So I'm really happy to be able to tell you this today. So here I would like to tell you also several experiences which we had through summarizing and gathering different experience of the members of the working group. What we can hardly see by Carl Fischer measurements is the seasonal moisture variation with temperature in a transformer. But we can see it very, very good when we have capacitive sensors. We can see the temperature variation, which is seasonal, and together with that, also the variation of moisture. Especially, this is very good to be seen in transformers with a certain cooling mode. For example, on-and mode will, of course, be better to represent this seasonal variation than direct mode of cooling. Another very important point is when we talk on capacitive sensors is where to install them. This is a crucial point because a capacitive sensor can deliver really reliable results only when it is in an oil flow. We can see on the left side installation in a cooler, which is a good installation because you have always moving oil there. And we have a certain, even at such an installation, you have a certain response time, which is about 10 minutes. It depends also on the type of sensor. And on the right side, you can see installation, which is in a pipe, which is far away actually from the oil flow. In such a case, you will have a very, very long time, if at all, to get a real reliable result. And the graph here is showing also the dependence of the response time to the distance of installation. So, I mean, it is not enough to have a capacitive sensor somewhere. It must be on the right place. Very, very important is when we talk on the importance and the influence of the moisture to know how the hysteresis curves of moisture cooling down and moisture again going back to the solid insulation is represented. Capacitive sensors which are online in a transformer, they do not only measure moisture in oil, they measure moisture in the solid system, in the system of both. Here we can see, for example, a dry insulation in insulating oil. And the hysteresis curve is very, very narrow because there is nearly no moisture which can go out and then go back. The situation will be quite different if we have wet insulation. And I would like to explain this curve. What happens here? First of all, we have increasing of temperature. That means that the moisture which is in the solid insulation goes in the oil. Oil which is hot can solve more moisture than cold oil. That's why the relative saturation is actually decreasing, as we see here on this arrow. What happens if we cool down now? The whole water, which is already in the oil and is solved in the oil, it goes back and tries to go in the solid insulation. However, when the oil is cooled down, the solubility of moisture is decreasing. That means that the amount of moisture in oil increases. We see here on the photo how the oil is getting turbid. And this is the most dangerous point. In such a case, of course, we'll have a very low breakdown voltage, which will immediately lead to breakdown. The problem is that actually the transfer of the oil is unpolar and paper is polar. That means that the oil which is solved in the moisture which is dissolved in the oil, it cannot go very quickly back in the paper. It tries to do that, but it cannot do it so quickly. Therefore, it's something like raining in the oil. This straight line, what you see here. After a certain time, enough time, of course, moisture will go back in the salt insulation, and you'll have again an oil which is clear, but it takes a lot of time. So this is actually in this graph, we can see that salt insulation, which is wet, has a very broad hysteresis curve. Again, going back to our curve, showing the dependence of breakdown voltage to water saturation. We can see here that we can have, in case of capacitive sensors, a kind of criterion which is acceptable. And this criterion are exactly these 20% which can be used for this purpose. On the next graph, I can show you a lot of graphs which are being taken out of real cases and which show that very clearly. On this graph, we have three major cases. The first case are the transformers just in the bottom, which are very dry. In this case, we have moisture which is much below the 20% as absolute value, relative saturation. And then the second thing, what we see here are very, very narrow hysteresis curves. The second case, these are transformers which are in service, which are safe, but which have, because of their long operation, some moisture. This is the second. There are two transformers just below this red curve of 20%. There again, both of them in absolute values below 20%, and they have again hysteresis curves which are not broader than 15% relative saturation. And we have the next case, actually the worst case, transformers which are wet. These are two transformers. One of them, we can see that relative saturation probe tank bottom. This is the dashed orange curve, and there is a dashed green curve which shows the same transformer, which is tank top. Both curves are over 20%, and we can see that the broadness of the hysteresis curve is about 20% and even higher. And one more transformer with a probe tank top. This is the blue one here, again with the same kind of evaluation criteria. We will have this these temperature curves, these hysteresis curves, also in the IC standard 6422 in the new edition, so that users can see this actually what happens really in a transformer insulation with and without moisture. So these are several conclusions which concern capacitive sensors. Capacitive sensors give us opportunity to develop new evaluation methods. As we saw already, they show us the dynamics of moisture between solid insulation and liquid insulation. And it is very important to have the transformer temperature, which is actually simultaneously also recorded by the capacitive sensors. And the evaluation criteria are about 20% relative saturation for capacitive probes, tank top, and 30% tank bottom. The broadness of the hysteresis curve is also an indication which can be used to evaluate whether transformer is wet or not. And of course, capacitive sensors must be specified, calibrated, and positioned correctly. And in our brochure, we have also very important parameters which must be determined. And I do not have time to talk on that today, but they show no temperature dependence, have a quick response time, have adequate sensitivity, and also be chemical compatible with different insulating liquids. Okay, if we have transformer, which is right, what can be done then in order to prevent breakdown and a fault? Of course, there are different kinds of schemes which can be used, what can be done when the breakdown voltage is low, whether water content is high, and so on and so on. It makes less sense to dry only once by degassing the liquid, because usually insulating oils do not solve so much water so that a transformer can be dried by it. Except this is a continuous mode. First of all, there is, of course, a method to dry, and this is drying by vapor phase in the factory. It's a very effective method. But of course, you must bring the transformer to the factory. It takes a lot of time. It is really maybe one of the most expensive methods. It delivers very good results, because then you can be sure that the solid insulation is really well dried. There are also drying possibilities on site. For example, low frequency drying is one of these possibilities, combined maybe with hot spray of oil. This takes also some time. It must be prepared properly. And yeah, sorry, someone talks to me. I heard my name. Okay, sorry. The transformer must be, of course, not only the low frequency heating is not enough effective. You need hot oil spreading or spraying in order to have a real good result of drying. Of course, there are different ways of dealing with this point of drying, but it is not always possible to do that. And the first thing to be done is actually to prevent the loss of the electric strength. And there are cases when the removal from service is impossible because of logistical reasons, or because it is not economical enough, or whatever. And in this case, of course, there are other methods which can be employed. For example, there are online drying equipment which can show, or which can very quickly lead to increasing of the breakdown strength in oil and decreasing the water content. Of course, this doesn't mean that the solid insulation is immediately dry, but a continuous using of such kind of systems, of course, can help to bring a transformer to an operating unit again on site with quite less economic efforts. So as a conclusion, I would like now to close my presentation here. Again, important things. Water solubility in oil is strongly dependent on the temperature. And that's why we shall always record the sampling temperature. Humidity and breakdown voltage are interdependent, and they must be both considered when evaluating moisture. And this is indicative only at service temperatures, because at low temperatures, actually the whole water is again in the solid insulation, and in oil you cannot see anything. The saturation, percent saturation, relative saturation in case of online monitoring, is a very, very good tool for evaluating moisture in the insulating system as a whole. And all remedial measures we can take against moisture have their merits and drawbacks, depending on the transformer conditions, and they're always a combination of condition, aims, economics, possibilities, and risk. So in closing my presentation, I would say that it would not have been possible without these people you see here and all these names. Everybody contributed to the results of this brochure, and I'm very thankful to them for that. What I want to say, we were happy 2018 to have groups of CIGRE which could meet in person. And I hope that one day it will be possible again, because it is very important when people know each other. And then this contributes very much also to understanding between different people, between different, understanding different way of thinking and so on. So thank you very much for your attention, and I'll be happy to answer questions at the end of this webinar if you have any. Thank you very much.
Great, thank you very much for that, Ivanka, much appreciated. Very interesting presentation. Pass on to Dan now to follow up.
G'day. So I take it everyone can see my screen and hear me?
Yes, yes.
Oh. So yes, I think it's great to have such a fantastic speaker as yourself, Ivanka. I mean, thanks very much for doing this. So we were, of course, wondering about time differences and whether we could make it work, but it was good. Fantastic happening. So, quick background to myself. So, I'm the New Zealand convener. I'm just going to look down. If anybody has their mic on, can they please just turn it off? There's a bit of laughter coming over in the background. Righto. So, yeah, quick background to myself. So, I was doing research at Monash in Victoria and then UQ in Brisbane. So, this presentation is really about what we were up to in those parts of the world. So, firstly, the inspiration here. Now, back in 2007, 2008, got involved when I was at Monash University with the sensors, and we were looking at measuring the water content of the paper. So I think this is quite a complex topic. There's a lot of things happening within the transformer, and it was interesting just seeing really how this all came together. So next, really in terms of the motivation. Now, the reason why we were so interested to have a good measurement of water, we had some other research happening at the time. So one of them was that we were developing models to improve the forecasting of insulation paper. Now, this requires the measurement of water. So this is where we got thinking about how do we improve things, how do we make the water content as accurate as what we really need be. Now that research ended up being used in the latest IEC loading guide. So it's great to see Australian science going into this international way of doing things. Now, also at that time, looking at water, we were investigating water bubbling in vegetable oil field transformers. So this was more looking at how do the properties such as density of the fluid affect the bubbling temperature. So when we were looking at this, one thing we did notice very quickly was really the errors. Now, we started off just taking samples of Carl Fisher with the oil, doing the KF on it, and then from that, just using some solubility curves and then working out the water content of paper. Now, when we were doing background reading to it, so there's been some work done by the IEEE, they're talking about up to 200% error is possible. And what we were measuring on this transformer, yeah, it seemed to be very like 200% error. The water content which we was calculating was varying anything from maybe 1.5% up to 6.5%. Now, water content cannot be changing this quickly in the transformer. It cannot be increasing and decreasing this sort of arbitrarily like that. So it gave us the idea, look, this is not really working quite right. It's dependent on the temperature. We do need better ways of measuring water. So when we got our hands on these probes, we were looking down at this table at these assumptions, and we were thinking to ourselves, well, how do we improve on some of these assumptions? And then we were relating it back into the water activity probe, these capacitive probes which measure the water content in the oil. And then we were just trying to, I suppose, negate some of these assumptions, or maybe clarify them, or maybe try and work out really how do we get around them. So the basic process to what is happening, we've got these charts up here. We've got our vapor pressure on the y-axis. We've got temperature on the x-axis. It is a function of water content of the paper. We have this equation. So it's not really quite, I guess, that people do notice that it's not easily to represent this whole graph using one equation, but perhaps that's good enough. Now, what we would do with our capacitive probes, or we sometimes call them water activity probe, is that we would take the water activity measurements, and then from that, if you know the temperature, you can work out this solubility, this pH value, and then you can work out this vapor pressure. So if we do that calculation, and then we can do another calculation on the Fessler to work out what the water content of the paper is. Now, probably the biggest disadvantage or the biggest difficulty is that this graph assumes that everything is in thermodynamic equilibrium. Now, we know that equilibrium is actually quite slow. So within our transformer, the temperature is usually changing all the time because the load is varying. So we're never really quite reaching this thermodynamic equilibrium. And then, of course, the next question, well, is that a problem? How do we get around of it? Can we have maybe error bars? So our research focused on resolving this issue, that if we're unlikely to obtain this thermodynamic equilibrium, then how do we do it? How do we still come up with our water content measurement? Now here we've got a graph showing diffusion time constants. So this is showing really how long it takes, or how long it indicates that we're going to take to get into this thermodynamic equilibrium. Now this is a time constant. This is not the time to equilibrate. So we might expect a few time constants to get near equilibrium. So this graph is really showing us that the migration of water between pressboard and oil is very slow. So if we were to put one of these capacitive probes in the oil, then it will, if the system is not in equilibrium, it will still take quite a while in terms of days or even weeks to start to get this tracking, this measurement here. Now, we started thinking about that. And again, we started wondering, how do we get around this? And we started thinking maybe we shouldn't be considering really a transformer as being out of equilibrium. Maybe we should be considering the pressboard inside as maybe pretty much fairly in equilibrium. You've just got these daily changes, or maybe a seasonal changes where the water is moving out slowly or moving back in slowly. Now this graph here shows one trace from a transformer that we took there. So what we can see here is that this is on a 24-hour cycle just of the load. We can see the temperature moving up and down. We've got the water content, the water activity, should I say, measurement from our probe, and it is also cycling. Now, what I mentioned before in that, suppose if rather than worrying about the transformer not being in thermodynamic equilibrium, maybe we sort of considered that it's pretty much in because the change in water content is so slow. And we're going to just get these very slow variations across the days. Now, if we were to think about that, or if we took that assumption as valid, then we can think about taking a long-term calculation of the water activity there, and then use that in our calculations to work out the water content. Now, that worked quite well. So we did publish that now probably getting on about 10 years ago. So if anybody wants more information of measuring water in transformers in this non-equilibrium conditions, then please do look up our publication there. Now, the next thing we started thinking about was that, okay, if we start off with this assumption that the water content of paper is probably overall this long period is probably not really changing that much. And all right, we can take the long-term average. But then we notice from this trace, so this is from a transformer, which is in the bush in Australia. And we have this seasonal effect on it. So this is moving into our winter. And what we can start to see there is just the temperature. So the temperature is changing there. The temperature is slowly cooling. So this is just our seasonal change, where we're moving out of the autumn in the deserts to the winter. So we thought to ourselves, well, if we've got this long-term change happening, then obviously a long-term average is probably not going to be the best because, well, it's changing. And where is this long-term average if it's moving? So we then thought to ourselves, wouldn't it be really good if we could actually update our method and rather having a long-term low-pass filter or long-term averaging function, suppose if instead we applied a low-pass filter to this, and we would want to actually remove these daily cycles and keep these long-term seasonal changes in the water content. So that gave us then the inspiration to look further in terms of the low-pass filtering. So the first thing we did was that we have here a transformer, we have here, we can see the temperature, we got a calculation of the water content of paper. That was taken from a capacitive sensor, put into it. Now what we did was that we wanted to see in terms of our signal, and if we are going to apply a low pass filter to it, then we just wanted to split the signal up. We wanted to see its spectral content. We wanted to see what frequencies are actually in there. So in terms of my graph on the right, what I'm showing is the spectral content of our signal. Now, we get a few points high up around 24 hours. That's where I put on the graph there, just a 24-hour cycle. So all I'm doing there is we're taking the signal, we've done the fast Fourier transform on it, and we're seeing we're getting quite a fair bit of signal around the 24 hours. Now, this signal is related to these 24-hour daily changes of the transformer. So we're thinking, let's get rid of these. We don't want that. We're more wanting to be looking at these very slow changes in water content, because I showed earlier the figure where we were showing how these time constants are affected by temperature and also these the thickness of the paper. Now we thought to ourselves, if we have a low pass filter, then how do we set things like the cutoff frequency? And we thought to ourselves, let's use some of these diffusion time constants. So we're then going to start by assuming that if we have a change in measurement, which is actually faster than the diffusion time constant of our system, then that's probably just noise, or it's like a temperature change or something like that, where we want to actually keep these very long-term slow changes in water content in our signal. Again, this work was published, so if anybody wants to find out further or have a longer read of it, then please do look us up. So I have here these three graphs. So the one on the left, this is plotting the water content of paper. And again, we're looking at the frequency at which this we got from the fast Fourier transform of the signal. Now, what I've done on the top right, I took the diffusion time constants of the water diffusing out of oily paper into the oil, and then we can just flip it around into frequency. So that's just 1/time. So we're now looking at something which is maybe more like a diffusion frequency constant rather than a diffusion time constant. And what we're now going to say is that if the signal from the water content of paper is changing faster than what the diffusion time constants tell us can happen, then we can filter that out. We can get rid of it. So we took here some values. We took the 30 microradians and we took a 5 micro. Now this was just looking back at our time constants of diffusion. We took the 30, which is maybe looking at the top end of temperature of our transformer. So we are taking the diffusion time constants at a fairly warmish operating temperature when the water content is going to be migrating fastest. And we're simply saying, let's filter out any signal which is faster than that. And then we were also trialing other measurements. So then we were looking at the 5 micro. And this was looking at, suppose if we have a lower temperature in our transformer, then we can use that in our frequency cutoff. So the graph on the left as well, I hope you can see the red and the green lines. So this is the general effect of our frequencies. We are saying we're going to keep everything to the left of either the red or the green line. Anything to the right is just either noise or it's the temperature changing too quickly. So if we keep everything to the left, then we should keep these very slow changes in moisture content, and then we can start to remove the daily fluctuations being seen by the sensor. Now the figure on the bottom right, so we're showing here, we've got our original data in blue. It's fairly messy. There's a lot of daily change in it. There's quite a few ambient temperature changes. We're then looking at filtering it. So we put the green line there and then the red line, and we're starting to see far better outputs of the sensor. Now, another thing which we get frequent comments about is to do with temperature correction. Now, when we started trialing our algorithms on industry's transformers, we were also using dielectric response as a way of just verifying that what we're coming up with is right, it's working properly. So one thing we very quickly noticed is that when we're using dielectric response, usually we are taking the temperature of the winding. In some cases, the transformer might be left to cool down because it has to be disconnected from the grid to actually do the measurement. So there's either two ways of doing the dielectric response. Either we've let it cool to ambient temperature, and then we know what the temperature of the winding is, or we might disconnect it and run the measurements and note down the temperature indicator. Now, nearly always in an operating transformer, the winding is slightly warmer than the oil. So that just means when we put these probes into the oil, the actual probe might be measuring a slightly lower temperature because the oil is slightly less than the winding. And then that means the way the isotherms work, generally, if you reduce the temperature, your water content of paper increases. So what can actually happen when we put the probe into the transformer is sometimes we measure more water in the paper and press board than the dielectric response machine does. And this is really just due to the differences in temperatures. So we did go away and we thought about this, and we looked at how to adjust the temperature and the water activity from the sensor to different temperatures. So this allows us to then, from the probe, we can do a recalculation. We can then, if we know what the temperature is around the winding, so this, if we don't have any form of measurement, it could be looking at applying an IEC thermal model that would give us an idea of what the temperature is, and then we can adjust the water content. Again, we published all this, so if people want to know the algorithms and calculations and everything, then please do go and have a look. Now, in terms of the degree of difference it can make, it does just depend on how the transformer is being run. If the transformer is being run at a higher load, then we might expect to see a higher gradient of temperature between the oil and the winding, which then just means we have more of an uncertainty in the water content of paper measurements. Now this graph here just shows an example of it. So we've maybe 0.5% less when the algorithm is applied. Now the importance sometimes is, well, the utilities generally have different limits of what they consider as when they have to take action. Sometimes it might be around 4% where the utility starts to think about drying out a transformer. But actually, if we apply this algorithm and we come down by 0.5%, then that might just mean they don't have to perform the operation yet. So maybe they can save themselves some money there. So this was another one of our test subjects, quite a big transformer. So we had 2 probes. We put one at the top in the pipe where the oil comes out to the radiator. There was one we put in to the return pipe back into the transformer. So what we were doing there is that these probes were both registering different temperatures, and that's just because one was in the flow of warm oil going to the radiator, and then the other one was in the flow of cool oil going back into the tank. So what we did was that we took the water activity measurement from both of them, we converted it into the water content of paper, and then again we did our adjustment. So in this case, the probe at the bottom, this is what we want to adjust more, because we want to be more reflecting of the temperature within the tank. Now, in terms of the temperature being measured at the top of the tank, we're probably going to be pretty close, maybe to the water content of the paper, to the temperature of the winding. It's just from that flow of oil going around. So we got quite a good close correlation there, and not only between the 2 probes, but also with the dielectric response. So they were showing pretty much the same value. Now these are some midlife transformers which we were looking at, and it was the same there again. We have our T1 and T2 are within the same substation. They're the same transformer, same age, same type, and we got very, very close to the dielectric response, which we thought was great. Now TR3 in this had actually undergone a dry out process. So, well, we're not going to expect the water content to be the same, obviously, because we've dried the transformer out. Also, what can start to happen on these on-site dry outs is that if we are drying out the oil, then it just takes some time for the water in the press bore to come out into the oil. So in this case, we usually expect the water content from the capacitive probe to be lower, just simply because we've dried the oil and now we're going to wait for all that water to come back out again. But in any case, we thought it was quite a good correlation, what we were seeing there. So in terms of summary, so the measurement of water is a very, I think, time-consuming complex. It's a lot in it. So we weren't really intending to go through everything. This was more perhaps the key points of what we think is important. So in terms of what we were doing in this presentation, it was more trying to take the potential sources of measurement uncertainty and explore them and come up with algorithms, come up with ways to try and remove them and improve the measurements. So all in all, I think the online moisture determination, it is a good one. It is also, I think it's fantastic. We don't have to take transformers offline. It's an online measurement, so we do have advantages there. So that's the end of my presentation. So thanks very much for joining. I'll now hand over to Dr. Baba Das.
Thank you, Dan. Can you hear me?
Yes.
Perfect. And you can see my screen, right?
Yes, we can. Yep.
Okay, perfect. So good morning, good afternoon, and good evening, everyone. And thank you, Dan and Ivanka, for the great presentations you have made. So I am Dr. Baba Das. I am from Hitachi Energy, from the Transformers Business Unit. And today I'll be discussing about the state-of-the-art transformer breathers. Before I go into the presentation, I just like to state that the main intent of this presentation is to promote a new line of thought. And the reason I'm doing this is because there are multiple vendors who are providing you solutions for state-of-the-art breathers. The end result of all the vendors are the same, and yet there are subtle differences in their operation principles. So I have kept the presentation vendor agnostic, and I'm only referring to a particular operating principle just for information sharing purposes. And I have used some assumptions in the calculations for the return on investment for smart breathers or maintenance-free breathers or dual column breathers or even self-dehydrating breathers. So you can call it whatever you like. I'm just referring it to as self-dehydrating breathers. And when you do the return on investment calculations, of course, you have to put in your own numbers. So as both Dan and Ivanka said, moisture is really crucial for transformers. And in this slide, I'm just highlighting that when the moisture in the paper goes up, let's say we have a dry transformer, less than 1%, and you are operating it at a hotspot of around 90 degrees, we expect it to last 30 years. But if the moisture goes up, the expected life of the paper goes down. And that is the reason why moisture is crucial. So I have been asked many times now that do we still need breathers? Because majority of the power transformers these days which we use, they have a air cell or a diaphragm. And when you have the air cell, it will keep the transformer dry from the air outside. And this forms the first line of defense against outside ambient air, which may have oxygen, which may have moisture. And technically, breathers are needed to preserve the rubber back from the effects of condensation. So in a sense, you can say breathers are the second line of defense, and they help to extend the life of the air cell more than the life of the transformer. But sometimes, as Ivanka pointed out, the material degrades, it gets ruptured, and it is sometimes during inspection, it is difficult to detect. And that is the reason why we still need the breathers. And of course, there are still many transformers in the world where they are without air cells and diaphragms. And that is the reason why silica gel breathers are extremely crucial, irrespective of the type of oil preservation system which we may use. Now, when we talk about the differences between the conventional breather and the self-dehydrating breather, there are some differences. First of all, maintenance. When we have a conventional breather, if maintenance is not performed or not performed regularly, there is a risk. Then you may have to do regular visual inspection of the silica gel and of course, handling. And then there is cost involved, recurring cost, because you need to store silica gel, you need to replace, you need to refill. And then you have the issue of disposing of. And there are some other environmental impacts. Now, silica gel by itself is non-toxic, non-polluting, the orange silica gel. But the main impact is the way it is produced. Now, if you look at 1 ton of silica gel, we'll need lots of sulfuric acid, sodium silicate, lot of water. So it is a very energy intensive process. And if you look at the 100-year global warming potential of silica gel, 1 kg of silica gel is equal to almost 4.12 kg of CO2 equivalent. And that is when it is produced under the European energy mix. So if you have silica gels, let's say from countries where the production is majority non-renewable, then this 4.2 kg will probably go up to 6 or 7. So when you start having, let's say you have 1 transformer which has 10 kgs of silica gel, and you do a 6 monthly replacement. So every year you need around 20 kgs. Then suppose you have 100 transformers in your fleet, that makes it 2 tons, you need 2 tons of silica gel every year, and you repeat this process for 30 years, then you will probably need around 60 tons. And that 60 ton, when you do the life cycle assessment, will translate to almost 240 tons of carbon dioxide. So there is a environmental impact. And apart from that, when we are disposing of the silica gel in landfill, we are just adding to the landfill, which we should try to avoid. And when we talk about the self-dehydrating breather, the advantages are you do not need to go for regular visual inspection. You can cut it down. You do not need to replace. You do not need to dispose. And you will see the status of what is the percentage saturation levels of the silica gel, and remote monitoring is also possible. And when we talk about the cost, if you do the total life cycle cost of ownership, there is a significant reduction in the cost. And of course, when we are using less quantity, because we are now regenerating the silica gel automatically, when we use less quantity, we are having less CO2 impact. When we are not putting it in the landfill, we are again having less CO2 impact. And when we are reducing our site inspection visits, I have seen cases where people are going to check the silica gel every quarter. Now, when we automate this process, we don't require our field crew to go long distances, come back. That will cut down on your global warming potential from the vehicles. If it's a petrol vehicle, or even if it's a battery vehicle, it will still cut down on the number of trips. When you cut down on the number of trips and you keep on accumulating over the lifetime of the transformer, that will significantly be reduced. Now, so what we are trying to do, we are trying to replace what you see in your left-hand figure. We are trying to replace the old school silica gel breathers with the new self-dehydrating breathers. And these can be installed either on the main tank or on the on-road tap changer. Now, there are certain benefits. Continuous online monitoring, of course, is one where you get to know the status of the silica gel. And the silica gel is automatically regenerated when it is necessary. And because we have 2 tanks which work alternatively, you have dry air going inside the conservator at any point of time. And typically these work well from -40 to 80 degrees. The electronic components, they have a mean time between failure of around 15 years. So if you are expecting 30 years of life, you will probably need to replace it once after the 15-year mark. And then, I mean, different manufacturers have got different layers of protection, different IP ratings, C4 protection. So all of that is available. So when we talk about how do we decide on the quantity of silica gel, that predominantly is determined by the quantity of oil inside the transformer, what is the average air temperature at the place of installation where the transformer is located, what is the relative humidity, and then the thermal cycle, duration of the thermal cycle, and when do you, how often do you maintain. So you can see the quantity of silica gel is directly related to the maintenance interval. So in the example on your right, I've just shown you one calculation. Let's say we have 80,000 liters and we have very high humidity, and we want to maintain it every 3 months. You'll probably need a lot more silica gel, which will add to your global warming potential, which will add to the total life cycle carbon footprint analysis of your transformer. And then if you reduce the maintenance interval, let's say from 90 days to 15 days, you bring the 62 kg down to 10 kgs. 10 kgs will dramatically reduce the carbon footprint from almost 250 kgs to 41 kgs. So depending on conditions, depending on how often do you want to maintain the silica gel, the size of the silica gel quantity of the breather and the quantity can be reduced by reducing the maintenance interval. And that is exactly what the self-dehydrating breather or the smart breather or the maintenance-free breather is doing. So again, in this example, I took some New Zealand conditions, and I say, okay, I will maintain my breather every 6 months. And if I do that, I can say I need for 80,000 liters, I need roughly 32 kgs, which translates to almost 1.2 kg of silica gel for every 3,000 liters oil volume. But then if I want to bring it down, depending on the maintenance interval, we can have lesser and lesser quantity. When we have lesser quantity, we are doing a lot for the environment. And the process is very simple. The idea is you just, the self-dehydrating breather will heat up the silica gel, the water will evaporate, and it is renewed. And typically, we expect 1 to 2 regenerations per month. So roughly, you can say close to 400 regenerations, which translates to almost 15 years of life. And when we talk about the quantity, the quantities are dramatically reduced. So from 30, 40 kgs, now you can do the same job with, let's say, 3 kgs or 2.5 kgs of silica gel. So you are not only reducing the quantity, you are actually reducing the landfill, you are actually reducing the related carbon dioxide footprint associated with the silica gel. So in this example, I have just taken the condition-based self-dehydrating breather. So here we have 2 tanks, tank A and tank B, and there is a valve which closes the path for either tank A or tank B, and then we have a load cell which measures the weight of the silica gel. So when it is breathing through tank A, the weight of the silica gel increases and the load cell measures that weight increase. And at a predefined set point, the tank A is switched off, the transformer starts breathing through tank B, and simultaneously heater is switched on so that the air, the humid air is taken out, it is heated, and the silica gel basically regenerates. And then the process repeats itself. This is the condition-based where we continuously measure the weight of the silica gel. Then we have time-based where you just set the time. You do not measure the weight or anything, you just set the time and say, okay, every 15 days, every month, the silica gel needs to be regenerated. So again, this is a coaxial tank. It is breathing through tank A. After a set time period, the heating starts for tank A and the transformer breathes through tank B. And again, the process repeats itself. So these are some examples. You can see now the silica gels are becoming compact, easy to install. And when we talk about the value proposition, as I mentioned before, you need to put your own numbers. But just to give you an example, let's say I have a 50 MV transformer. I expect the life to be around 25 years. The cost of silica gel is around $18 per kg, and the labor cost is around $85. And I have 10 kgs in that particular transformer. And I go for 4 times every year to do the inspection, and it takes me like 30 minutes to do my visual inspection, and I can replace it in 1 hour. And then when you calculate the cost, you see for 25 years, the lifetime cost is around $30,000. Then when you shift from the traditional breathers to the self-dehydrating breathers, the initial purchase price may go up by 6 to 8%. So let's say if your original breather was around $300, now you may spend around $1,800. And over a lifetime of 25 to 30 years, you will probably need 2 such breathers because of the MTBF. So the lifetime cost is roughly $3,600. So if you compare over a period of 25 years, you see that you were spending $30,000 and now you are spending around $3,000. So the cost saving is around $27,000 per transformer. And if you have 100 such transformers, you'll end up saving around $2.7 million. So it depends on what is your labor cost, how much time it takes for inspection, how much time it takes for replacement, what is the cost of silica gel, where you are buying it from. All of that, once we do the calculations, it is clear that for self-dehydrating breathers, the total cost of ownership is much lower than the conventional breathers. And when we scale it up, we did an exercise for one particular utility where we scaled it up. They had like 14 300 MVA transformers, 300 MVA, 68 75 MVA transformers, and 460 MVA transformers. And then we calculated the total maintenance cost over 25-year period just to maintain, replace, dispose silica gel came out to be around $4.1 million. And then when we replaced it, when we replace it twice over the same period, with a self-dehydrating breather, it is costing around $425,000. And the savings is around $3.6 million, and the payback is in less than 3 years. So there's a very good return on investment if we adopt this maintenance-free breathers or self-dehydrating breathers or smart breathers. And then we also calculated what is the reduction in carbon footprint for site inspection. Now, for this particular site, we used a value of 0.187 kg CO2 equivalent per kilometer for a petrol vehicle, roughly for a 2000 cc petrol vehicle. And then we calculated every time I need to go to the transformers different distances, but the average distance was around 40 kilometers per return trip. And based on that, for 25 years, if I just go for my maintenance of the breather, the life cycle carbon footprint adds up to be around 89 tons. Now, when we have a self-dehydrating breather, I'll probably go once, and I'll probably go, we will tag it for some other purposes as well. So we are able to reduce the additional carbon footprint just for traveling purposes. And if my inspection frequency is higher and the distances traveled are greater, here I'm saying that we are only going 20 kilometers up and 20 kilometers down. But if you travel more, obviously your GWP is going to go up, and that adds to your life cycle assessment of your transformer. So when we talk about self-dehydrating breathers, the final summary is we can do continuous online monitoring of the status of what is happening to my breather. It is a very good cost-effective way to monitor the transformer's condition. Easy installation and maintenance. Maintenance is significantly reduced. And then now in the market, we have lots and lots of new state-of-the-art breathers, which gives you the possibility to connect these devices to your SCADA system via different Modbus, analog outputs, and then you can now have a good understanding of your entire fleet of what is happening with your transformers. And finally, once upon adoption of this technology, upon reduction in the actual amount of silica gel which we are using in our transformers, that leads to significant reduction in the global warming potential factor which comes from the self-dehydrating breathers. So that's all from my side. Thank you very much, everyone.
Great, thank you very much, Dr. Babadas, for the presentation. So that wraps up the 3 presentations. Now pass over to Judith. Are you online there to coordinate some of the questions?
Hi, Matt. Yes, I am.
Great, thank you.
So there were quite a number of questions for Ivanka. I just start with the first one that came through. I have no sound. Okay. I just read Andy's message that he doesn't have sound.
Oh, okay.
Well, I hope it's just him. So you can hear me, Matt. So I am assuming
yes, I can
others
hear you.
can
Yep.
as well. Okay, so the first question that Brad put in the chat was around the curves that you showed, Ivanka, appeared to be in the opposite direction. with the relative saturation of the oil body increasing as temperature increases, and he's asking why this might be the case. I'm not sure if it's maybe helpful to jump to that slide which he's referring to, if that doesn't take too long. Or you, yeah.
I think that maybe you will get my email address. Maybe we can discuss this point, because I need to see these curves. I've never seen actually a hysteresis curve in the representation relative saturation to temperature, which is broader at the high temperature. So it will be helpful for me to understand this point, to see these curves, and we can discuss per mail, because otherwise it is a question which cannot be answered directly. I mean, I must see the particular case.
Okay, so how do we do this? Then do you forward Ivanka's email, or?
Yes, I think that it will be fine if we contact per mail with the person who asked the question. He can show me maybe these curves, and we can discuss on that, because for me it is not, I cannot judge on that before having seen the case.
Okay, yeah, no, that's fine. So Brent, maybe if you could maybe just share your email address, or ask maybe Matt to pass on or get Ivanka's email address, and I think you can send her the details. That's okay.
Yeah.
Yep.
Yeah.
Certainly.
Okay.
Do that.
Sounds good. Another question that was raised by Willard was whether there are any recommendations to measure the relative saturation in case if there are no online sensors.
This is a little bit tricky thing, and I'll tell you why. Actually, if you take a sample and bring it in the laboratory, it has another temperature. And automatically, of course, it has another relative saturation. The point is also that if you take a sample out of a transformer, you don't have a solid insulation inside. The relative saturation and these recommendations, which you saw in the presentation, they are valid when you have the system solid insulation oil, and this is only in case of transformer. So out of a transformer, it is very difficult to make really judgment on relative saturation, because the conditions are different. We talked a lot of time during this presentation that moisture, breakdown voltage are dependent on temperature. And if you don't have the temperature in the transformer, but just room temperature, the evaluation criteria are more or less those
I think we might have lost you.
Oh, yeah.
Ivanka. Maybe it's the headset.
Can you still hear us, Ivanka? Or?
Notice that her microphone's active in the Goethe
yes,
meeting,
okay.
but we can't hear.
Maybe we just give it a minute or so in case she's reconnecting the headset.
Sorry, did you have
Yes. Yes, we're back. Yes, we can hear you. Yeah.
I mean, shall we repeat again? Or did you hear that, what I said?
Yeah, to a certain point, we heard you. Yeah.
Actually, what I said is that one shall be very careful if such kind of exercise is done, because the temperature in a sample taken out of the transformer is different, and it doesn't reflect the conditions there. So these values or limit values or evaluation criteria, they're valid for relative saturation online.
Okay, thank you for that. I
Great,
think
thank
that's a great answer. Okay, and another question that came through from Alex was about whether oil samples, DGA results from the laboratory are usually in ppm at a given temperature, and he's asking whether this can be converted into percentage of relative saturation.
I mentioned that we dealt with this question of transferring relative saturation in ppm. This is possible only if you have absolute equilibrium between the in the transformer operation. And secondly, when you take a sample for DGA and do DGA, this is done again in the laboratory, and it is done at room temperature. That means that you don't have again the temperature which you have in the transformer itself. And therefore, even if you transfer it mathematically to percent saturation, it will not represent the conditions you have in the transformer. Again, it is very important that relative saturation and its evaluation criteria, if we want to evaluate both solid insulation and oil, shall be done online. Offline evaluation of moisture, please then follow the standards, for example, which exist for that. For example, IC 6422. They give more recommendations for that.
Okay, that's great, thank you. I think that was also the answer to another question that we had around whether there are any standards such as the IEC 60422 as a guidance for the relative saturations, which is what you just referred to. I'm not sure if there are any other standards or if that's the main one.
Actually, as I said, 6422 gives, first of all, the evaluation of the historical evaluation of moisture by Carl-Fisher titration. But in the new edition, which will appear this year, I hope, we will find again, for the first time, the evaluation criteria for online monitoring.
Okay. Thank you. One more question. Okay. I just read it out as it was put in the chat. Okay, please indicate if the markers represent the time intervals used on the hysteresis curves. If not, do you have an approximate heat up or cool down speed?
This is a very good question. Actually, what you saw on the first example I showed, I mean, this was more or less a laboratory test to show in a very rough way what happens, is done very quickly. It is very, very important what is the rate of heat and rate of cooling. If the rate of cooling or heat are slow, even wet transformers have chance to survive. Because it is the question of how quickly moisture can go back to solid insulation, or how quickly can moisture go out of the solid insulation. At slow increase rates, this takes place slow, and moisture has time to have kind of equilibrium and not oversaturate the oil. But when this heat up or cool down happen quickly, then
we lost you again, Ivanka, I think. No, I'm pretty sure I can't hear you anymore. I see you're talking. Your mic is still working.
may I suggest we move to another question?
Yeah.
Yep. Yeah, that sounds good. There was one question that just popped up in the chat for Dr. Baba. Yes. Oh, he just answered in the chat. So I just read it out. There was one question in regards to the last presentation that we saw, and the question is whether we still need to test the insulation resistance of the transformer with SDB installed, and if there's any chance on the any change on the pre-commissioning testing. Sorry. And the response to that was yes, absolutely, no change. Does this answer the question? Or do you want to elaborate on that a bit further? Thomas or Baba?
Yep, that's fine. Thank you.
Okay, thank you. Okay, and then there's one last question that I would just read out. Looking at the apparent commonality that all the insulating liquids have their graph percentage relative saturation versus breakdown voltage, would this indicate that the percent RS has a very important wetting effect on particles in the liquid? Or is it believed that the pure but wet liquids would behave in exactly the same way? So that question from memory was to Ivanka. I'm not sure if you're back online.
Yes, I think
a really long question.
Okay, I think that
yes,
particles are, of course, a topic for themselves. All these topics or evaluation criteria, they are, of course, have the presumption that no significant amount of particles is present. If particles are present, of course, they decrease very rapidly the breakdown voltage. But usually, particles are present actually in case there is a very strong degradation of solid insulation, or there is another problem in the transformer. I mean, then the values will be much, of course, they are valid. However, the breakdown voltage will be in a bad situation because of the particles. This is more or less the case that no significant amount of particles is present, which will decrease breakdown voltage.
Okay, thank you. And then there was, that's all the questions that were put up in the chat, but there was one comment made, which I just would like to read out because I actually experienced the same at work. Someone, I think it was with it, put in the chat that he said that they would like to use the percentage RS instead of water content and ppm, but no one agrees with him because people are usually more familiar with water content and can't imagine about percentage RS when they make a decision about red paper. And that's, I guess, could be a comment to everyone, to all presenters as well.
I would like to say only, if you try to use percent saturation under laboratory conditions, you need a capacitive sensor. Capacitive sensors, in order to work properly, they must have always a very big flow of oil. This is difficult. And they need also a very big response time. So I am skeptic that one can use capacitive sensors under laboratory conditions successfully. The results will be quite different. And additional, you have the problem that you don't have the temperature in the transformer. So to be honest, I would not recommend using relative saturation for samples which have been taken from a transformer brought in a laboratory. But of course, this is my opinion and my experience.
Okay. Any other comments on that? Okay, thanks for that. There was a question for you, Dan. Does the thermal loss calculation of the paper on probably relate to standard 60076-7 NXC?
Probably. Do you have any more clues to the question, Thomas, mate?
Yep. Sorry, Dan. I mistyped some words. I was just asking.
Yeah, I wasn't. I couldn't figure it out
yeah.
while I read it out. I tried to.
Yeah, I'm so sorry. I had a long
No,
day.
no, that's all good.
So from the graph, the DP values, as the DP values decreases, obviously the transformer lose more ages, has higher life losses. Is it reflected into the the life loss calculations on the NXC of the standard?
Yeah, it is. Now, I would just say of the latest IEC standard, it is. Of the Australian/New Zealand version, that's behind, and it doesn't really do it that well. So I'll just say, look at the IEC one.
Yep, cool. Thanks, Dan.
Cool. Well, in that case, we're pretty much on time now. So I'd like again to thank Ivanka from joining in.
There's one last question.
One last question.
Dan?
Go for it.
Yes, sorry for interrupting. Yeah,
No,
just hope we probably can squeeze in one more question. A lot of companies suggest online drying out. It measures water content in oil in and out of the device. How do we know water in paper? And when do we finish online drying out? The question is posted in the chat as well.
I think what I've seen in the past, and this is just how we did it. I mean, there might be other better methods, but you do a bit of drying out and then you turn the online dryer off, and then the water content of the oil slowly increases again, just as it's transferring out the paper. Now, we did it over about a year, just to give everyone an idea of the time it was taken. So it was just about taking the dryer off, waiting for the water content to increase again, put it back on again, let it fall again, and doing that 2 or 3 times, and then it wasn't changing any further. I know that I don't know how recent findings are, but I remember reading some guides from about 10 years ago, which did warn about paper cracking if it was dried out too much, because the paper would shrink, and if it's too degraded, that it might break or crack. So I'm not really up to that, but I don't know if anybody else has any comments.
Yeah, I would make a comment. Actually, this is very good. Generally, it's like that. We talked about danger of moisture. The first and the most, the worst danger of moisture is that you have low breakdown. And if you have online drying, the first thing you're doing with your online instrument or device is to dry the oil. Of course, this gives you the possibility to operate the transformer further. Depending what this device is, it can take more water when the transformer is warm, so it is always there. I don't think that it is in such a case, when you are doing online drying in such a case, it is very, very important to know what is the water content of the paper. Important is that you have reliable operating conditions. And drying over the oil is always a long process. It will not be finished within a short time. And the best way to understand whether you have still water in the salt insulation is what Dan said. You can shut it or you can circuit it after a certain time when you have stable conditions and look whether water is coming back. If water is coming back, that means you need further drying. Usually online drying devices require longer time, they are milder, and they actually allow reliable operation. because of the breakdown voltage.
Good points, Ivanka. And to add to that, online dryer, as you say, is a milder drying process. It ideally is keeping a moderately dry transformer moderately dry. It's probably avoiding going into the territory of a very wet transformer and looking at more onerous, more expensive dryouts with the attendant need for addressing reclamping windings. And so an online dryer doesn't take you back, try and take you back to 0.5% with that sort of consideration of reclamping needed. It's just bringing it back to say 1.5% reasonable operating state, and with a softer drying process without that loose clamping, reclamping need to be done with that sort of drying.
Yeah, actually, I don't know what is your experience, but usually our experience is that power transformers are usually very, very seldom wet, very seldom. The problem is more or less with smaller transformers. Some of them do not even have dehumidifiers, and very often such kind of procedures are not really economic. Big drying is not economic for small transformers, but such kind of equipment, which is drying slowly, is economic because, as you said, they are small devices and they can be moved from one equipment to another.
Yeah, agreed.
There are no more questions.
Okay.
Then, Matt?
Great. Yeah, I think that brings us to the end then. So, well, thank you very much to all our speakers who have either started very early or stayed back late to balance out the time zones and shared some great information with us. Yeah, and I guess thank you very much for attending, all the attendees, and just keep an eye on the CIGRE website and LinkedIn pages for any future events that the A2 panels may be holding. Dan, did you have something you wanted to add?
I just wanted to thank Ivanka again because just being prepared to get up in the morning and stuff. And yeah, we did put this web tube back a couple of weeks just to make good use out of clocks changing. So I'd just like to say thanks very much again. It's great to have you as our international speaker.
Thank you very much to all of you and all participants as well. Thank you.
Thanks very much.
It was really very, very nice. Thank you.
Okay.
Thanks very much, everyone. Cool.
Thank you, everyone.
Bye.
Bye. Talk to you next time.
Yeah. Stay safe. Bye.
Thank you. Bye-bye.